this short live stream for at least beyond, no, not beyond, less than 30 minutes. Oh my god, it's happening. Okay. So this is derivation of the Boltzmann constant from ideal gas equation and from the Avogadro number. Okay, this one. Okay, pressure times volume is equals to the number of moles times universal gas constant times capital T. Pressure in terms of 101,025 Pascal, and then 1 Pascal is equals to Newton per square meter. Newton per square meter, okay? And the volume will be in terms of cubic meter, so that it will be cancels out. Okay, and then what cancels out are the meters for that. And then for the number of moles, small letter n, universal gas constant, joules per mole Kelvin. Joules because joules is also Newton meter, so it will agree on the left side. Okay, for the pressure. And then capital T is Kelvin. 273 Kelvin because that is standard temperature and pressure. Temperature is 0 degrees Celsius. So all you have to substitute here in this PV is equals to nRT is meeting the STP. Okay, quantities that are meeting at STP. So pressure 101, 325,000 Pascal. Volume is 22.4114 liter of gas volume it will occupy at an ideal air or an ideal gas, okay, like that. So our R is 8.3145, okay, something like that. And then the T 273.50 degrees Kelvin, okay, actually Celsius plus Kelvin, okay, so 0 degrees Celsius, automatic 273.15 Kelvin. Okay, now we have the equation of the number of moles, small letter n is equal to capital N is equals to over capital NA. So NA is Avogadro number. The Avogadro number in chemistry, as far as we could remember, okay, that is Avogadro number 6.023 times 10 to the 23 per mole. Okay, like this. Okay, guys. Okay, this is the Avogadro number 6.023 times 10 to the 23 per mole, or mole raised to the power -1. It's just the same. Okay, with 1 over mole. Now our capital N will be the one molecule of an ideal gas. Okay, so let's substitute values now. So pressure is 100,001,325 Pascal. We go directly to Newton per square meter. Okay, like this. Okay, and then volume is 22.414 liter. This is the standard volume, okay, that an ideal gas will occupy at 0 degrees Celsius and at 1 atmosphere, or 101,025 Pascal. Okay, so this is the taken from Avogadro law. Okay, he is the one who postulated and discovered this theory at STP. Okay, something like that. Okay, since we have liters, we need to convert that to cubic meter directly. Okay, so like this. So 1 liter is equals to 1,000 cubic centimeter. Okay, like this. 1 liter is equals to 1,000 cubic centimeter. Now, in every 1 meter, there is 100 centimeter. So, both raised to the power 3, so that it will have cubic centimeter in the denominator and cubic meter in the numerator. Okay, so that it will cancel out the denominator. Okay, so 100 centimeter, then 1 meter. So as you can notice, it will be cancelled already. Okay, agrees already the units for this, and then like that is equals to the number of moles. Universal gas constant is 8.31. Okay, 5 joules per mole Kelvin, and then the temperature is 273.15 Kelvin. Okay, like that. It's gonna be like that. Okay. So we use directly the R here. Actually, this is also the same as N over NA times R over T. Okay. This part here. Okay. Okay, because if we divide, okay, the N over NA, and then we have obtained here in the equation, so this will come out like this. It's just the same sterling, okay? Like that. If you substitute the capital N over NA from the number of moles here, it will just the same story. It will yield an equation like this. Okay? Okay, so cancels this out. So since there is still more left here, then we need to multiply this by 1 mole of an ideal gas. 1 mole ideal gas. Like this, so cancel, cancel, cancel. So what left here is the, okay, what left here is the joules. Because Newton is kilogram meter per second squared. Okay? Like this, Newton. Newton is kilogram meter per squared. So Newton. So convert, and then you can obtain the values. Okay? Like this. So N is equals to like this. Okay. So cancels, right? So what we left now is joules. Okay, 8.315 times 273.15. Okay, and the upper portion will be 101. Okay, 101,000. Okay, 325. Okay, and then 22.414 times 1,000. Okay, and then this divide 1 over 1 million. Okay, so this is our number. Actually, this is the number of moles pa siya. Okay, so if it's N, it's the number of moles. It's okay. Then, if it's a number of moles N, then we don't have to multiply it with mole pa siya, so that it will agree. Okay, it's gonna be like that by visual inspection. Okay, or else we need to divide, multiply with 1. But still, we are finding here the N. Okay, like that. So N will be how much? So 1 over 1 divided by 1,000 is 2.01 times 1 divided by 1 million, right? Times 1,000 times 22.414 times 100, 1325 equals to 2271. Okay, 2271. 2271.09855, right? Divided by 8.3145 times 273.15. Okay, so 2271 1056. So our N is 1 mole. Okay? 1 mole of an ideal gas. This is our N. It's in here. Okay? Like this. We solve for the value of N small is 1 mole of an ideal gas, in which it is equal to our theory, which is 1 mole of an ideal gas. Okay? And then since we know that N is equal to N over Na, let's substitute again in the PV and RT. Okay? Right? So it was proven that it's 1 mole of an ideal gas, right? Now, we have the small letter N. Okay, and then we now again substitute the value of, in this equation, capital N over Na. Then, so pressure times volume is equals to capital N over Na times R times T is 1. Okay guys, it's gonna be like that. And then by theory in chemistry, Boltzmann constant is equals to R over Na, the universal gas constant over the Na. So we will rearrange this equation as PV, okay, R, Na, and T. Okay, and this is the Boltzmann constant. Okay? PV and RT, right? So small letter N is capital N over Na, and then R over Na is the Boltzmann constant. Then put that in the equation. Your Kb now will be equal to Kb, Boltzmann constant, pressure times volume divided by Nt. Okay? Guys, our N here, okay, our N here is simply, our N here is equals to N times Na, in which we solve the N already here. The small letter N is 1 mole of an ideal gas. Actually, we don't have to solve that because at STP, we just proved that one so that we can use that in here. So, capital N over Avogadro number is equal to small n. This is 1 molecule of an ideal gas. So, 1 molecule of an ideal gas, or capital N, is equal to N times Na. Okay? Cross multiply in the algebra. So substitute that N times Na here in the capital N. Okay? So Kb is equals to pressure times volume. Okay, we have N times Na. Okay, this comes from the equation N is equals to N over Na. I showed to you so that it's very clear to your naked eye, something like that. Okay? So, Boltzmann constant is equals to N times Na times T, pressure times volume, because coming from this equation. Okay? Now, substitute values already. Okay? So, at ideal, gas, at standard temperature, pressure, at estimate. So, pressure, again, just like this, values here. Changing the number of moles, the same thing. Okay, so pressure 101,035. Okay, and then volume 22. Copy everything here because this is just the same story. All units will be constant. Copy the numbers only. Okay, we don't have to put everything because it's just numerically equal. Okay, the units or the numbers also. So V is equals to 22 when 414 letter, and it's gonna be like that, 1000. And then in here also, okay, since this is pressure volume, so 1 over 1,000, okay, 100. Then it's gonna be 1 million automatically, okay. So N, we solve already N as 1 mole of an ideal gas, or simply 1 because it's TPA. Okay, so 1 mole, then times the Avogadro number. Avogadro number is 6.023 times 10 to the 23, right? It's gonna be like this. Okay, so this is gonna be now compute Okay, so this is gonna be like this, times 101.325.2414, and then 6.023 exponent 23 is equals to, okay, like that. And then the answer will be, our Boltzmann constant is 1.38 times 10 to the negative 23. Okay, the unit will be in joules per Kelvin. Okay, why? It's very clear here, guys, during the cancellations. Here, everything will be cancelled here. And what's left here is joules in Kelvin also. Okay? Like that. Malong, because Newton meter is joules here. We left here is Newton, and then meter we left here somewhere along the way. Newton meter is joules, and then Kelvin like this in the denominator. And it will be cancelled because there's a 1 mole also in the denominator. Okay, so our unit will be joules per Kelvin. Actually, guys, the unit of Boltzmann constant is just the same in entropy. You remember entropy? Entropy also has a unit of joules per Kelvin. Okay, identical unit. Okay, like that. So, or we can simply say also KB is equals to R directly over to NA to make it simplified. This one. It's just the same story, guys. You don't have to substitute in the PV and RT. You just use Boltzmann constant is equals to universal gas constant divided by the Avogadro number. So I will show you. So KB, using this equation, another simplified formula, rather than using the PV and RT, because PV and RT is more tasky, or it consumes a lot of time when you derive it from PV and RT. So it's better to use this other option. Boltzmann constant is equals to capital R over NA. So R is universal gas constant that we are using every time, okay, which is 8.3145, okay, like this. So substitute 8.3145 joules mole Kelvin. Okay, divide A, so Avogadro number 6.023 times 10 to the 23 mole. So mole will be cancelled and joules Kelvin left. So this is still the same. Guys, even though you will not use the calculator, you will just move the exponent to the top. So it will become times 10 to the negative 23. Divide this first. This 8.3145 divided by 6.023 and obtain that number, and then just put that times 10 to the negative 23 by algebra. If you transpose that to the numerator, the exponent will be negative. The same as if you transposed the exponent to the denominator, it will also become negative if it's positive. Something like that. That's the rule of algebra. Okay? So, it's gonna be, divide na natin siya diretso. 8.3145 divided by 6.023. So, that is 1.38. And then, add times 10 to the negative 23 because it will be transported to the top. So, it's the same value here, equal also to here. Okay? So, our KB is equal. From using the simplified KB is equal to R over NA, and by using also PV is equal to nRT. Okay, it's very clear, right? So all you have to do is to memorize the number of mole equation, okay, which is the capital N, 1 molecule of a gas over NA Avogadro number, and then insert that there, or you use also directly the formula KB or Boltzmann constant is equal to universal constant R over NA. Okay, something like that. So why we need to determine the Boltzmann constant? Because the Boltzmann constant is very important in transition state theory, in chemical reaction kinetics. Because guys, if we have a reaction A plus B, for example, that is a one-step chemical reaction to produce a product which is primarily AB, of course, right? Bimolecular chemical reaction. Two reactants. That's bimolecular. Okay. Now, it is very important because somewhere along the way, in the middle of your chemical reactions, there are intermediate and stable reactions also in between. Okay? For example, this calculator is your reactant, and then plus the pentyl pen, it will produce a cell phone, something like that. So somewhere along in the middle, it there will be a they will play a game within the chemical reaction before producing a product. Something like it will take time to produce the product. So in that in between chemical reactions, there's a lot of unstable intermediate. So the intermediates unstable are what we call reaction intermediate reactants plus intermediate reactions of the product. Okay, this intermediate reaction reactant, will be having a band. You know, band Bond. So could either be a covalent band, non-polar covalent band, van der Waals band, hydrogen bonding, H2H bonding, if you can remember in chemistry. Okay, somewhere along in the middle of the chemical reaction. Now, it would have a proper orientation first, and correct orientation at an correct angle with each other before it will produce a product. And not only that, this will contain an activation energy or sufficient energy to react with each other. So there are requirements in between the chemical reactions. Now, this intermediate reaction, since it contains a reactant, bonds, and contains also intermediate reaction bonds of the product. Intermediate reaction bonds of the product. Bonds is BOND. And still the same, hydrogen bonding, van der Waals bonding, and polar covalent bonding, and then it will partially produce a product. Okay, and then this reactants also partially break the bonds to produce the partially reaction product, to form. So in between, before it will go a real product, which is AB, from A plus B. Okay, there's a lot of, there will be a lot of chemical reaction will be happening before producing the one-step chemical reaction. So in that situation, why it is playing around in between the chemical reaction, so it will achieve a transition state theory or transition state between the chemical reaction, which is the highest point of activation energy has been reached. Okay, so at that time, very strong reaction, and the time will come at time period, let's say 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, it will slower down also the activation energy, and it will goes down like that. It goes down, and then it will develop again the activation energy, because the activation energy is a minimum amount of energy requires to start the chemical reaction. Something like that. And take note, the activation energy is regardless of a catalyst or not. Okay, because even though there's no catalyst, there's so many chemical reactions will proceed without catalyst. Okay, so that means activation energy without catalyst. So that is what we call uncatalyzed reaction. Okay, and activation energy with catalyst is catalyzed reaction. So your uncatalyzed reaction is greater than your catalyzed reaction. If you try to look on your graph, I don't have to illustrate the graph because as I told you, this is a short live stream. Okay, if we will having a time, we will discuss to you one by one for that. And there's also a lot of activation energy will be somewhere in the chemical reaction. Okay, as I told you, there's a lot of intermediate reactions, the products and reactants that will either produce partially, the products, and either break the bonds partially also. Okay, but there's a lot also of activation energy equivalent to each intermediate reactant, reactants, and products. So activation energy is equal to E1, E2, E3, E4 until such time it will stabilize to the total lowest or minimum activation energy to produce the final product AB from A plus B in a one-step chemical reaction. So you get the point now? So something like that. So the chemical reactions in between. So the transition state theory there in between is what also we call as activated complex state, or what we call also as an absolute rate complex, absolute rate state, something like that. So it's gonna be like that. So for example, in the future examination, there will be a question like this. Blank is a transition state period. Okay, what is another term for this? So there's a lot of choices there. Your answer will be activated complex state or absolute rate state. Another term for transition state. That is the highest minimum, no, not minimum, highest na. It's the highest activation energy needed in between the chemical reactions to produce unstable intermediate reactions. Okay, because it's not yet in the product, kaya nga unstable siya. Okay, so that's the logic behind for that. Okay, so it sounds to be not really experimental, that's hypothetical because you're just analyzing what's going on in between. Hypothetical or more theoretical. Okay, the more actual understanding is to produce directly the product, right? Normally, if you go into the laboratory, and then you mix a lot of chemicals, you are going to see the products, right? In your naked eye after that. So somewhere along in between the chemical reactions there, so you cannot see, okay, how the molecules and particles bombarded with each other to develop the activation energy and will proceed the chemical rate of reaction and how we can determine how fast or slow the chemical reaction really is. So it's gonna be like that for transition state theory. Guys, so that would be enough. The next vlog will be talking about the equation of Eyring and Polanyi equation. This is very important also because this deals with energy diagrams. Okay, energy diagrams to understand the Gibbs free energy or the internal energy versus the reaction rate, okay, or the extent of the reaction. Guys, in chemistry or in physical chemistry, you have to analyze different terminologies because in the examination, it will come out really the another terms for this, like this, and somewhere along the way, it will change the question, not really word for word, something like that. Okay, another term for reaction rate would be also a rate law, as I told you over and over again in the introduction of my discussion of chemical reaction kinetics. And it's also called, guys, a reaction coordinate. And it's also called as a reaction progress. And it's also called as the extent of the reaction. So there are four terms to be used, right? To plot that versus the energy. And the energy in the y-axis could also be either a potential energy, an internal energy, a potential energy. So the energy there is being also not word for word all the time. Sometimes energy only putting, sometimes potential energy, sometimes kinetic energy, sometimes gives free energy. As long as it is an energy, because this is energy diagram for the y-axis. What I mean is that not literal, okay, most of the time. So you need to troubleshoot the different terminologies involved so that you can understand really that this is gonna be like this, and you can plot directly what is being required, and you can obtain the correct graph for that. Okay, in that graph we can understand what's happening with the reaction rate, the rate constant, okay, the number of collisions or the collision frequency resulting in a solution, something like that. Okay, what will be happening to the temperature if you add that one to your chemical reaction, if you add catalyst, okay, if you add the concentration, if you to change the surface area, okay, of your container of your chemicals mixed together, if the particle size of reactants will be changing also, and also the nature of the reactants matters a lot also. What do you mean by nature? The physical properties. For example, if you add sodium ion, which is an electrolyte, plus chloride, so you need to know that this chlorine is highly negative particle, will react to the positively charged particle sodium. So it will matters a lot the behavior before they will react and to produce a product. That's why in that manner, we need to determine the kind of bonding they will produce so that we can determine how strong and how fast the chemical reaction really is. So nature of the reactants also are very important. Okay, not only the temperature, pressure. Again, factors affecting the chemical rate reaction: temperature, pressure, concentration, okay, the nature of the reactants, okay, the surface area, okay, and the particle size. Particle size of the reactant. Okay, the surface area of the container. So, for example, if your container is very having a small diameter, they will easily collide with each other, right? Because it's very, it's very congested. The distance is very limited, so they will just bump with each other because there's no enough space. You get the point? So something like that also, you have to correlate the area for that. Okay. So if there's a pressure is equals to force over area, and if the area is very small, so you need a high pressure in order for the collisions to proceed faster. Okay, and then if the high pressure will be there, and then your volume will become lower. Okay, because volume is directly proportional to the area. The more it will become lower the volume, of course the area also will become lesser. Okay, volume and area. Okay, something like that. So you have to understand the relationship properly, because this is very important in the E-ring and what's it called about? Polyani, sorry, it's very difficult, right? Okay, E-ring and Polyani equation in 1935, their collaboration between the relationship between the reaction rate and the number of collision frequency of the four particles and the molecules in a chemical reaction with respect to the change in the temperature. Something. It's related to Arrhenius equation, but this is more, shall we say, more accurate compared to Arrhenius equation, really, as far as my research concerned for this. E-ring equation and E-ring and Polyani equation in 1935 is more effective a little bit compared to the Arrhenius equation in 1896. Okay, so this Henry E-ring, first name Henry, E-ring is the last name, have a collaboration with Michael Polyani, like that, in 1935. That's why the equation what was named from them. That's in 1935. So 1896 to 1935, how many years it took the discovery of this E-ring equation? It took a lot of years. I have my calculator, I will subtract. So 1896, 1935, okay. 1935, you are not born yet. Okay, 1935 minus 1896. Okay, it took 39 years for Mr. Henry E-ring and Michael Polyani to formulate a theory that states the reaction rate of the chemical reaction is dependent to the temperature and also to the number of particle collisions, okay, per unit time, something like that. So this is only the introduction part. I have to discuss the detail regarding transition state theory so that we can understand package siya, and then we can derive another equation, which is the E-ring and Polyani equation in 1935, something like that. So if there's a problem related to this like this in the future examination or board examination, then you can answer also, because it's not always equation, Arrhenius equation all the time, really. Okay, because sometimes Gibbs free energy will be present, enthalpy will be present. So what's the magic for this chemical reaction kinetics? We can input also the physical chemistry and the thermodynamics, really. Because if you have the reactants, if you have the products, then you have also the enthalpy change for that. Okay, and then we can identify if it's an exothermic reaction also. But it is very important to draw. I don't have time anymore. Later I have to draw that one. Where can we project the enthalpy change and the Gibbs free energy? And through the data or analysis of the Gibbs free energy and the enthalpy, we can also note the entropy change for that. So in that manner, we can easily analyze if the reaction or if the chemical reaction favored to the reactants or favored to the forward rate of reaction, or we can say that the reaction or the chemical reaction favored to the reactants or the rate of backward reaction. Something's gonna be like that. Okay, so in here you can troubleshoot which is a reversible chemical reaction or irreversible chemical reaction somewhere along the way. Again, with your transition state, okay, with the highest amount of energy there. Okay, there's a lot of rate constants and we will be enjoying that much. Okay, and then we apply also the theory of Arrhenius in plotting into the graph. The yes again Ln of the concentration, and this temperature also is just always like that, guys. Concentration and the temperature. Basically related to the Arrhenius, oxy, Airing, and Pugnali. Okay, but there's a little difference because it's a little bit accurate. The 1935 theory of Airing and Pugnali compared to the Arrhenius equation. But the credit also will be given to Arrhenius equation because without Arrhenius, Svante Arrhenius in 1896, these two guys cannot create also their scientific research because they also derived that from Arrhenius, Mr. Svante Arrhenius in 1896. Okay? And Svante Arrhenius, okay, his scientific discovery was superseded by Henry Airing and Pugnali in 1935. Then, at the time also, another scientist, Mr. Ludwig Boltzmann, appeared for that. Okay, because that rate constant, Mr. Ludwig Boltzmann used that also in his theory regarding entropy. That's why you will see that there's a K, okay, an Ln, an R, and T in the formula of entropy, the randomness of the system and the process. And it states that the sum of all the entropy will be increasing. So this also Boltzmann, that's why the Boltzmann is very important also in the Airing equation, right? They're very related because that's the reason why. Okay, so if not, there will be no KB or Boltzmann constant somewhere along the way that could be substituted in the equation of Airing and Pugnali, right? It's gonna be like that. Okay, so just memorize for now, guys, the basic equation, and then we can derive something new, a little bit complicated equation by graphing. Okay? Because this is for experimental study talaga siya, not really focusing on stoichiometric relationship. Okay, something like that. So at least we know already the stoichiometric relationship and the experimental study to compute problems solving in chemical reaction kinetics. Okay? Oh my gosh, it's happening now. I have 5 minutes more. Okay? Something like that. So be careful. So memorize na at early this time. Boltzmann constant, Kb is equals to 1.38 times 10 to the negative 23 joules Kelvin. Okay? And then we introduce also another constant, the Planck constant. After Boltzmann, Ludwig, another also scientist named Planck's constant. Mr. Planck also after Boltzmann. So there's a lot of science, and after that there will be also Helmholtz, and after Helmholtz there's also Mr. Rudolf Clausius. Okay, my gosh, in the first law of thermodynamics. And after that also there's also a discovery of heat engine principle and cyclic process of Clausius-Clapeyron. Oh my gosh, the overall cyclic process of a heat engine. Clausius-Clapeyron is second law of thermodynamics. So it's gonna be like that, guys. They are always related with each other, and they're also sometimes fighting with the theories and concepts like that, and then they will commit suicide, something like that. Because based on my research, Ludwig Boltzmann died because of that issue. Okay, because another scientist superseded his theory, and then something like that he cannot really accept, whatever, and then time will come, he cannot accept, due to depression, he died. Okay, something like that, and another scientist came in, so like that, so problem. Okay, a lot of scientific research and competition before in their era, really. Okay, so it's gonna be like that. So that's the Boltzmann constant. The Avogadro number also 6.023 times 10 to the 23 per mole negative. Actually, the Avogadro's number, it depends on the problems you're asking for. For example, if it is an ion, so that will be also per ion. If it's a formula unit, so per formula units. If it is molecule, so per molecule. Something like that. It depends on what is being required, as long as there is a 6.023 times 10 to the 23 and you know how to apply it. Okay, like that. And then that's capital NA. And then the Planck's constant is 6.63 times 10 to the negative 34 siya. Okay, so memorize also. It has to do something with the same in protons. You know, remember the mass of protons and electrons, right? Something like that. It's really a little bit related, I think so. For that, and then there's derivation, it come up for that. So until it arrive that value related to electrochemistry, something like that. Okay, so you need to dig it out also why, and then connecting the dots, something like that. But you know, it is very tasky to connect the dots. Really, it's very tasky, and then sometimes your brain cells will be tired. Okay, especially if you memorize, and then sometimes you'll be a little bit confused, like this, like, so all you have to do is to understand na lang talaga the basic concepts so that you will never be confused. Okay, during your memorization. Okay, something like that. Okay, very clear na ha for our derivation for Boltzmann constant versus the Avogadro number. Okay, so later we'll be deriving the Eyring and Pugnale equation in the transition state theory. Okay, so like that. A lot of sources will be used also. Do not depend on one source so that you can understand properly. Go to 3 sources, 4 sources, 5 sources, and find the most, easy to understand approach. And then, because you have already the stock knowledge, right? And then, then you will be able to derive it, review, like that, right? And then you can understand also. Okay, something like that. So after this derivation of Eyring and Pugnale equation, before we will go to the electrochemistry, because the next topic that we will be able to discuss is the electrochemistry. Okay, producing electric current by having a chemical reaction. That's electrochemistry. That's only combination, electro plus chemistry. The chemical reaction involved in producing electrical energy or electricity. Okay, that's electrochemistry. Okay, thermochemistry is a chemical reaction to produce a heat energy, which is the thermal energy. That's why thermochemistry. Just like that, the technique is just like that. Okay, petrochemistry is also a chemical reaction involving the raw material petroleum. That's why petrochemistry. Okay, that's the technique. Petrochemical are chemical products derived or driven by the raw materials petroleum again. That's why it's called petrochemicals. Okay, so it's gonna be like that. You will troubleshoot the terminologies first so that you can really understand and then apply your stock knowledge about sciences in your high school and in grade school level. Because it's very important to be used in the college. Okay, so that you will never struggle in college. Okay? If that is the case, you want really a course related to sciences, But if your course is not related to sciences, there's no problem. Okay, with your course related to money matters, business accountancy, College of Arts and Sciences, psychology, political science, broadcast journalism, which I like the most. Okay, mass communication, banking and finance, something like that. You don't have to worry about these formulas in sciences. Now, if you try to take a course related to sciences, then you have to undergo an adequate and thorough memorization of science formulas and equations from your elementary level to high school. Okay, because this will be used over and over again in college also. That will be your weapon to understand properly and clearly in college. Because if you just understand that in college, then something, you will be left behind, something like that. Because for me, acquired knowledge and stock knowledge is the best. Okay? You will just keep on adding that one as long as you have the stock knowledge and acquired knowledge already. Okay? Something like that. And you have to explore more. Something like that. Okay? It's gonna be like that. As I told you over and over again, a scientist or a science related to engineer should be equipped with critical thinking and wild imagination. Okay, plus the application of the technology and mathematics. Okay, so that will be the definition of a legit engineer and a legit scientist, something like that. So have qualities like that. But the scientist is more on the scientific research because they are very observant. Aside from the quality of having the mathematics and the practical application of technology, so they are very observant and they're very have the passion of extensive scientific research. Those are scientists. But for the engineers, even though you don't have a scientific research, full scientific research, as long as you have the wild imagination and then you have a critical thinking with the application of mathematics and technology, then it's okay. Okay, but you don't have to worry about scientific research. But what I mean, if you want to become a scientist, work more on scientific research. Okay? So that's why in America, in United Kingdom, for example, if you're a graduate in BS Chemistry, and then if you work for a laboratory as a BS Chemist, okay, your category will be called sometimes as a scientist. Okay? Scientist 1, Scientist 2, Scientist 3. But in Asian countries, you will never call that kind of job as a scientist. Okay? So there in Western countries, scientist is a position or a job designation. Okay, not necessarily mean that you are like Isaac Newton, okay, you are like Avogadro, you like Antoine Lavoisier, the father of chemistry, you like Alexander Newberg, the father of modern biochemistry, you like George Davis, the father of chemical engineering, like that. It's not like that all the time. As long as you are a graduate of a related science course and you work in a laboratory and then your job really undergo scientific research and then you will become a scientist by designation. Okay? Not really that kind of labeling compared to the Isaac Newton. It's not like that. Okay, in Asian countries, USA, UK, Europe, except for Asia. Okay, Asia will never call you a scientist after you graduate in chemical engineering, and you're a chemical engineer. After you graduate in chemistry, you work in a laboratory or whatever, they will never call you as a scientist. They will call you just a laboratory analyst, okay, or a technical analyst, a product analyst, or a chemist, something like that, or a chemical engineer, something like that, or a process engineer, something like that. But they will never call you as a scientist in Asia. But in the Europe countries, they have very unique terminology for all science courses graduates who work in real world also in scientific research and in the labs. Okay, so you see the difference? It's more fulfilling, right? If somebody will call you a scientist, oh my gosh, the leveling is very A, class A. Okay, like that. I researched that also. That's why. Okay, something like that. Okay, it's gonna be like that. Okay, in fact, my classmate in chemical engineering, his job before is also an ink scientist. His designation. Ink meaning they formulated the raw material of the ink, and then if you are working for that section, you will be called a scientist. Okay, he is ink scientist. Wow. Or toner scientist in his designation in his ID, because he works in UK now, and now he became a manager there in United Kingdom. Okay, in the same specialization, ink or toner in computer. Okay, he's also a graduate of chemical engineering. Okay, or my classmate. Okay, something like that. Other one also is my classmate, chemical engineer also. He's now an instructor of chemical engineering in UK. Wow. Okay. He's very intelligent. Okay, he's always our top notcher, whatever. Okay, he's now an instructor in UK teaching physics, chemistry, and chemical engineering subjects. I don't know what university is. I will ask later because we have we have group chat. Okay. So international instructor because he finished his education units and PhD in physics Okay, an engineer, chemical engineering or something like that. Okay. Okay. Thank you so much for watching for this short live stream. I hope you found this interesting, and you can comment down below in the comment section. You can subscribe the YT channel of mine, and then you can also share this to anybody else if you are interested. And then you can click for some newest updates of I Am a Singer channel voice regarding science formulas, equations, chemical engineering, sciences like that. But not so much with mathematics. Anyhow, mathematics will be also included in the discussion sometimes, right? Usually algebra, calculus, something like that. But not really those difficult calculus, only the basic. The natural logarithm, plus one. So the slope in algebra, the y-intercept, wow, slope, okay, like that. Then the graph, you have also to understand that a little bit. A little bit now because I'm not a student anymore, right? I'm working now in the real world as an OSH engineer. I'm just trying to do this because I want to increase more my knowledge for sciences, and at the same time, I want to vlog because I have a YT channel. Okay, so I don't have anything in my mind that it's comfortable for me to vlog. Really, guys, just I don't think anything. Because I found it boring to vlog cooking, to vlog outing. It's just like, it's very easy to do that. Okay? But for me, I found it challenging to vlog like this because it needs you critical thinking. Critical thinking meaning you have to sharpen your brain just to have this kind of content in YouTube. Right? If you compare this to YouTube, which is only a comedy, sports, and cooking, right? Ang sobrang layo talaga, di ba? It's very easy to do that compared to this. Okay? Though my approach in vlogging and live streaming is boring, I know that, I accept the fact. But if you try to follow it from first to last, then you found it enjoyable, especially if you love science and if your course also related to sciences or engineering. Okay, so that's it. Sometimes also I like to vlog cooking, but I found it, boring because I don't love to cook also. That's why. And then personal vlogging, what I mean, you do exercise, dancing, singing a little, a lot during my Fridays and Saturdays. I do a lot of singing moments, right? So, but dancing also sometimes. But what I mean, I really need to think, to sharpen my brain cells. Really. Okay, because I don't know, really after 3 or 5 years or whatever, we don't know. I don't know what's my destiny. It's God's plan for me, okay? Maybe I could be able to become an instructor, something like a professor, or doctor, or whatever, in chemical engineering, whatever, right? So we cannot guess. We cannot predict our future and our destiny. Wow. Okay. So in short, okay, let's just enjoy what's now. Okay. Thank you so much for watching for this, guys. Okay. Bye bye, Soma. Bye bye to everybody. God bless everybody. See you later for the next topic. Okay. Another equation to be derived. Okay. Thank you so much. Wow. Charot.